This video will cover section 9.3, which will talk about the integral test for convergence or divergence and a p-series. So first of all, we're looking at series and tests whether they converge or diverge. So the next test that we're going to learn is the integral test, which involves obviously taking an integral. Now, we have several different tests because we have so many different series, and each test can only work for certain types of series. So the integral test will only work if f is positive, continuous, and decreasing for x greater than or equal to 1. Okay, so positive means above the x-axis, continuous, and then decreasing for x greater than or equal to 1. So if we have that, then we can apply the integral test. So what that means is if we have a series, so some summation of a sub n, and then we take the integral, and what the relationship is here is that a sub n is going to be the same as our function. So if we make a sub n a function of x and then take the integral from 1 to infinity, and we talked about this in the last unit with improper integrals. So if the integral from 1 to infinity is convergent, then the series is convergent, and if the integral is divergent, then the series is divergent. Okay, but again, it only works for series where that a sub n is positive, continuous, and decreasing for x greater than or equal to 1. All right, so for our first example, determine whether the series converges or diverges. We have the series n over n squared plus 1. Now, just to show you that this series does match all of that, the positive, continuous, and decreasing for x greater than or equal to 1, I graphed it just so that you can see this. So here's the graph of that f if you make it x over x squared plus 1, and you can see for x greater than or equal to 1, it's positive above the x-axis, decreasing, and continuous. Okay, so since that matches, then we can determine the convergence using the integral test. Now, I would always kind of think about the nth term test, just kind of in the back of your head. So that is if the limit as n approaches infinity of n over n squared plus 1, if you think about that, and you don't have to write this down, but just thinking about the nth term test before we move on and try other tests, it's pretty simple. So the limit of that would be, if we applied L'Hopital's rule, we'd get 1 over 2n, which then would approach 0. But we don't have to apply L'Hopital's rule here because this is a polynomial over polynomial. So we could have just said low degree over high degree, therefore the limit is 0. So therefore this is inconclusive by the nth term test. So since we can't use the nth term test on this one, it's not a geometric series, so we're going to apply the integral test. Okay, so the first thing that we're going to do is we're going to make this n over n squared plus 1. We're going to make that a function of x, and we're going to look at the integral. So looking at the summation, it's going from 1 to infinity. So we're going to look at the integral from 1 to infinity of x over x squared plus 1. And then using our integration techniques from the last unit, we're going to find the integral of this improper integral. All right, so the first thing we want to do is when we have an improper integral, remember we want to take the limit. And so we're going to take the limit as b approaches infinity of the integral from 1 to b. And then we're going to have to use u substitution for this integral. So we want to make u be x squared plus 1, and then du would be 2x dx. And so we have the x sitting up here, but we need to take care of the 2. So then that would be 1/2 du equals x dx. All right, so since we have that 1/2, I'm going to put that 1/2 out in front of the limit. And then I'm going to do my u substitution. So this would end up being 1/2 times the limit as b approaches infinity of the integral from 1 to b of 1 over u du. Okay, so now we want to take the integral of 1 over u, which is fairly easy. It's just the natural log of u. And I'm just going to go ahead and do my u substitution. So the 1/2 limit is going to stay, and this is going to be the natural log of u, where u is x squared plus 1. And notice that my x squared plus 1 is not an absolute value because x squared plus 1 will always be positive. Therefore, with the natural log, it does not need the absolute value. Okay, so now we're going to evaluate this. So evaluate the upper limit b minus evaluate the lower limit 1. So again, we have 1/2 times the limit as b approaches infinity of the natural of b squared plus 1 minus the natural log of 2. Now as we take the limit as b approaches infinity, this natural log of b squared plus 1 is going to approach infinity. So this whole thing is going to approach infinity. All right, so if my integral is approaching infinity, that means that my integral is divergent. So you could just put divergent here, but therefore, since that equals infinity, then my integral diverges. And since my integral diverges, then by the integral test, we know that the integral and the series are going to both converge or both diverge. So then, since that integral diverges, therefore the series itself diverges by the integral test. Okay, so for our second example, we have the series 1 over n squared plus 1. Hopefully you know by intuition that this is matching all of those descriptions, positive, continuous, and decreasing for x or n greater than or equal to 1. But just in case, I have the graph here if you want to see. So greater than or equal to 1, this graph is all of those things. All right, so we're going to apply the integral test here because, again, if we do the nth term test, then this would be approaching 0, therefore inconclusive. It's not geometric, so we're then going to apply the integral test. All right, so the first thing you want to do is you're basically just going to rewrite the summation as an integral from 1 to infinity, and then you're going to make it in terms of x instead of n. All right, so then we're going to evaluate this improper integral. So again, we're going to have the limit as b approaches infinity. And then to evaluate this integral, we don't have to use u substitution. Hopefully you notice the format here, 1 over x squared plus 1. That's going to be arctangent. So now we're looking at the limit as b approaches infinity of arctangent of x, evaluated from 1 to b. So then we're going to evaluate. We're going to plug in arctangent of b minus arctangent of 1. And now as we approach this limit, hopefully you remember the graph. So if you envision the graph of arctangent, then it has horizontal asymptotes at negative pi over 2 and pi over 2. So as b approaches infinity of arctangent of b, we're approaching pi over 2. And then minus arctangent of 1 is pi over 4. So we have pi over 2 minus pi over 4, which is then pi over 4. So since this integral is approaching a finite number, therefore this integral converges. Now the integral converges to an area. Remember, if we're taking an integral, we're finding an area under the curve. That approaches the area of pi over 4. However, the series is not equivalent to the integral. They are not equivalent. So the series, if we were to sum up the series, it will not equal pi over 4. That's important. We know that it converges since the integral converges, but it does not approach pi over 4. And in fact, as it says at the bottom of your notes there, it says the sum of the series is always greater than the value of the integral. Okay, so again, since the value of the integral is pi over 4, then we know the series converges, but it converges to a value that's greater than pi over 4. Okay, so now what I want you to do is I want you to try number 3 by yourself. So please pause the video, try it by yourself. It's good to remind yourself how to integrate these improper integrals and go ahead and prove whether this converges or diverges by the integral test. I will go ahead before you do that. I will go ahead and show you the graph of 1 over x natural log of x, and again you can see for greater than or equal to 1, this graph is positive, continuous, and decreasing. All right, so pause the video and do number 3. Okay, so applying the integral test, we have 1 over x natural log of x. So u here would be natural log of x, du is 1 over x, and then from there it follows pretty naturally. So we have so when we do u substitution, we have the integral of 1 over u, which then is also natural log of x, and natural log of u would be natural log of x. Now this does have to be an absolute value because natural log does have the possibility of being negative. Now, of course, not on the interval from 2 to b, but just in case we put it there. All right, so then you should have done this. So you apply or evaluate that from b to 2. And then as b approaches infinity, then we get infinity. Therefore, the integral diverges, and therefore the series itself diverges by the integral test. Okay, so hopefully you were able to get that pretty well. So now we're going to look at a p-series and what that looks like and how to tell whether a p-series converges or diverges. Okay, so a p-series is actually quite similar to a geometric series. So we have a series of the form 1 over n to the power of p. So whereas a geometric series was like a ratio to the power of n, this is just the opposite. We have 1 over a constant to, oh sorry, not a constant, our variable to some power. So this is called a p-series, so we would have, as n changes, 1 over 1 to the p, 1 over 2 to the p, 1 over 3 to the p, and so forth and so on. And p has to be a positive constant here. Now, if p is equal to 1, that means we have the series 1 over n. So that's 1 plus 1/2 plus 1/3. We've seen this series before, and before we were able to take the nth term test, and we found that that equals 0. And we talked about this before as being a divergent series, but we weren't able to show why yet. And actually, this is something that you need to memorize, is that this is called a harmonic series. So a p-series where p is equal to 1 is called a harmonic series. And remember, we said that this diverged, and so a harmonic series diverges. Sorry, this is really big. Okay, so that's really big for a reason, because that's definitely something that's going to be tested on, is knowing what a harmonic series is and knowing that a harmonic series diverges. So again, harmonic series is a p-series where p is equal to 1. So essentially, it's the summation of 1 over n. Okay? All right, now just kind of an extra note here. This is not something you need to memorize, but a general harmonic series is the form 1 over an plus b. Notice that that's like a linear function. So 1 over n is like the main harmonic series, but any linear function where I have a degree of 1 is called a general harmonic series. And it's actually pretty cool because you see this a lot in music, because strings of the same material, diameter, and tension, whose lengths are different and form a harmonic series, produce harmonic tones, which is pretty cool and something that you can research on your own if you'd like. Okay, so what we're going to do is we're going to first use the integral test to determine whether these p-series converge or diverge. So the first one we have, this is a p-series. We have 1 over n to some number, and that p is 1/2. All right, so this is a p-series where p is 1/2, and we're going to use the integral test to determine whether it converges or diverges. Okay, so first of all, we're going to talk about the integral from 1 to infinity of 1 over x to the 1/2. And now when I integrate this, we're going to take the limit as b approaches infinity, and I'm going to go ahead and rewrite this as x to the negative 1/2 so that it'll be easier to integrate. So this is just the power rule of integrals. So we're going to take that negative 1/2 and add 1, which would be positive 1/2, and then multiply by a multiple of 2. Okay, so the integral is 2x to the 1/2. Evaluate that from 1 to b, and then take the limit. So we have the limit as b approaches infinity of 2 square root of b minus 2. And so as b approaches infinity, this is just going to approach infinity. Therefore, the integral diverges, therefore the series diverges by the integral test. Okay, so this was a p that was less than 1. We've already been told that, or I told you that the harmonic series where p is equal to 1 also diverges. So p less than 1 diverges. So let's look at when p is greater than 1. Okay, so for our final example number 5, we have the series 1 over n cubed. So that is a p-series where p is equal to 3. So if we apply the integral test for this p-series, then we'll have the integral from 1 to infinity of 1 over x cubed. And I'm going to just go through this really quickly. And then we have the limit as b approaches infinity. And I'm going to rewrite that as x to the negative 3. And so when I take the integral of that, add 1, we get negative 2 with a coefficient of negative 1/2. And then evaluating that from 1 to b, we have negative 1 over 2b squared plus 1/2. And now as b approaches infinity, it's in the denominator, therefore this first thing is approaching 0, therefore we're approaching 1/2. So again, the integral is approaching 1/2, therefore the integral converges, and then therefore the series converges. But remember, it's convergent to something greater than 1/2. Okay, so this leads us to a p-series, and how to tell the convergence or divergence of a p-series. So if you have a p-series, 1 over n to the p and nothing else, that means not 1 over n to the p plus 1 or minus 2, just 1 over n to the p. If it's just that, then you can tell the convergence if p is greater than 1, then it converges, and it diverges if p is between 0 and 1, which is the opposite of the geometric test. Remember the geometric series, if r was greater than 1, it diverged, and if r was less than 1, then it converged. So this is something that a lot of people get confused with the geometric series, so just make sure you have the p-series and a geometric series clear in your head. So really quickly for our last thing, what I'm going to do is I'm going to show you, for example, 4 and 5, since these were p-series, we used the integral test to tell whether these converge or diverge, which is fine, but these are also p-series. So since these are p-series, then we can now use knowing our knowledge of the p-series, whether it converges or diverges. So if this was a test or something like that, I would not use the integral test for 4 and 5. I would use the p-series, which would look like this. So for example 4, we would state that we know that this is a p-series with p equaling 1/2, so very similar to how we would describe a geometric series. So this is a p-series where p is equal to 1/2, which is less than or equal to 1, therefore divergent. So as long as we include each of those parts, we know it's a p-series. What is p and how does it compare to 1? And then therefore we know it diverges or converges. So a lot simpler than the integral test. All right, and then for example 5, we had the series 1 over n cubed. That is a p-series with p equaling 3, which is greater than 1, therefore we know it's convergent. Okay, so example 4 and 5, it's very easy. P-series, just like geometric series, are our friends because they're very easy to recognize and to tell whether they converge or diverge. The only thing with a p-series that's different from a geometric is I cannot tell what it actually converges to. So if we do the integral test for a convergent p-series, we can see what it converges greater than, but not what it actually converges to. Okay, so let's go back really quickly and look at the first few examples. Number 1, just to show you, this is not a p-series, so therefore we had to use the integral test for number 1. Same with number 2. Number 2 is very close to being a p-series, but it's 1 over n squared. And so that one, or n squared plus 1, sorry. So then that one's not a p-series because of the plus 1. And then number 3 obviously is not a p-series either. So we can only apply the p-series test if you have the just strict p-series. Also really quickly, for the p-series 1 over n, where n is equal to 1, or p is equal to 1, all we have to say, we don't have to say p is equal to 1. Let me show you on the p-series. If p is equal to 1, then we know it's divergent. But if we had the integral or the series 1 over n, all we have to state is it's harmonic series, therefore it diverges. That's it. The AP test recognizes that a harmonic series is divergent, so that's all you would have to state for the series 1 over n. Okay, so those are 2 more tests, the integral test and the p-series test, to add to your list. So far we have the nth term test, geometric series, p-series, and integral test for testing series for convergence or divergence.